Welcome to The Explainer. Today we're going to talk about something that's just magical, right? We're diving into the science behind these huge, gorgeous machines and how they just float. And you might be surprised at how simple and ancient that science really is.
Okay, so let's just get right into it. You see one of these things, right? They're enormous. And you find out it can weigh over 800 kilograms. That's like a small car. So how in the world does it just float? It feels like it's breaking the laws of physics. But the secret? It's not about defying gravity. It's about mastering a really, really old principle. Yeah, and the answer, believe it or not, doesn't start in the sky. It starts in the water. Over 2,000 years ago,
You got it. We're talking about the one and only Archimedes. You know his famous eureka moment in the bathtub? Well, that single discovery laid the groundwork for everything. And centuries later, it would be the very thing that literally lifted us off the ground.
I mean, think about that. This one idea, this single aha moment, it's the bedrock for all lighter-than-air travel. From the earliest, simplest hot air balloons right up to those giant airships you still see sometimes.
Okay, so this is it. Archimedes' principle. It's the key to everything we're talking about today. Basically, it says that anything you put in a fluid gets a little push upwards. And the key thing to remember here is that air is a fluid, just like water. Have you ever tried to push a beach ball under the water at a pool? You know that feeling, that strong upward force pushing back at you? Well, that's the buoyant force. And here's the cool part. The strength of that push is exactly equal to the weight of the water the beach ball is pushing out of the way. So you can basically think of flight as this simple battle, right? It's a tug of war. You've got the downward pull of gravity, that's the object's weight, and you've got the upward push of buoyancy. Whichever force is stronger wins, and that determines whether you sink or you fly. And it really is this constant battle. For a hot air balloon to get off the ground, that upward buoyant force, what we call lift, just has to be stronger than the balloon's total weight pulling it down. It's as simple as that. Okay, so that's the principle. But how did we get from a theory about stuff in water to actual human flight? Well, for that, we need to fast forward way forward. And that brings us to these two brothers, Joseph Michel and Jacques-Étienne Montgolfier. They were paper manufacturers back in 18th century France. The story goes they were watching laundry drying over a fire, and they noticed how the fabric would puff up and rise. Now, they actually got the science a bit wrong. They thought the smoke itself had a special lifting property they called levity. But that wrong idea, it sparked a world-changing invention. I mean, just look at this timeline. It's absolutely incredible. In less than a year, they went from a tiny little box experiment that just hit the ceiling to putting actual human beings in a basket and having them fly for almost half an hour over Paris. The pace is just staggering. And get this, while all this was happening, there was a completely different technology popping up, a rival. While the Montgolfiers were messing with hot air, a guy named Jacques Charles was working with hydrogen gas. So you had this amazing race to the sky with two totally different methods. And Charles was right on their heels. He got his first human flight up just 10 days later. So, okay, we've come a long way from basically burning wet straw under a big paper bag, right? So how did we get to the sleek and, let's be honest, much, much safer balloons we have today? Well, a huge piece of that puzzle is the burner system. The burners on modern balloons they're marvels of engineering. They use propane for this super intense, fast heat. But the most important thing, the thing that really matters, it's all about safety and redundancy. We're talking multiple burners, dual igniters, separate fuel lines, all these layers of protection. Because when you're thousands of feet up, you want to know for sure that it's going to work. And this whole process happens in a flash. The pilot pulls a trigger, liquid propane vaporizes, it shoots out, and whoosh, a huge flame roars to life. That chain reaction is what gives the pilot such amazing control. Every pull of that trigger is a direct injection of lift, letting them tweak their altitude in real time. And it's not just a simple on-off thing either. Pilots have basically two gears. You've got the main blast flame. That's the loud, powerful one you hear for big moves like taking off or climbing fast. And then you have what's called a whisper flame. It's quieter, more gentle, and it's perfect for making those tiny, precise adjustments to just hang at the perfect altitude. Okay, so this is probably the question you've been waiting for. If all you can do is go up and down, how in the world do you steer the thing? Well, this is where ballooning goes from simple science to a real art form.
You're right, there's no rudder, no propeller, nothing. You can't just turn left. So what a pilot has to do is learn how to use the sky itself as a giant invisible steering system.
Think of the atmosphere as having different layers, like a cake, and each layer has wind moving in a slightly different direction or at a different speed. They're like invisible rivers in the sky. So a skilled pilot knows, okay, the wind at 500 feet is going east, but if I climb to 1,000 feet, I can catch a current going northeast. By going up and down with the burner, they can literally choose which river to ride. And that is why you almost always see hot air balloons flying right after sunrise or just before sunset. It's because that's when those wind layers are the most stable and predictable. Once the sun gets high in the sky, it starts heating the ground, creating these unpredictable columns of rising air called thermals. And those thermals just churn everything up, mixing all those nice layers together and making it impossible to navigate.
So what's the target temperature inside that giant balloon? Well, it's usually somewhere around 120 to 130 degrees Celsius. That's the sweet spot. It's hot enough to create a ton of lift, but it's still well within the safety limits of the fabric. You don't want to damage the balloon after all.
So when you really get down to it, a hot air balloon isn't defying gravity in the slightest. It's just being incredibly clever. It's using basic physics to create this huge bubble of air that's way less dense, and because of that, way lighter than the ocean of cooler air all around it. And look at that, we're right back where we started. With Archimedes, a hot air balloon floats for the exact same reason a giant ship floats on the ocean. It has made itself lighter than the fluid it's pushing aside. It's a 2,000-year-old idea, and it is just elegantly simple.
And what's so cool is that this principle works in any fluid. So think about this for a second. On a planet like Venus, the atmosphere is so incredibly thick and dense that if you had a balloon filled with just our normal, breathable air from Earth, it would float. Our air would be the listing gas. It kind of makes you wonder, right? Where else in the universe could we fly just by understanding this one simple idea?